Humans have always been dissatisfied with their lot. Life is all too brief, and our short span on Earth burdensome. For 1,000 years, these harsh realities spurred the alchemist to search for an elixir to prolong youth. One of the elixirs of this century is a class of chemicals called organochlorides. Beginning with World War II, the insecticide DDT was mass-produced, and it's estimated that 1 billion people were spared the ravages of malaria. Then followed the development of polychlorinated biphenyls, or PCBs. Chemically inert and possessing high boiling points, these compounds were used as transformer coolants and flame retardants. In 1961, Rachel Carson, in her book Silent Spring, blew the whistle on the indiscriminate use of pesticides. Poisons that killed little things were also killing big things. The very property built into the pesticides, namely long life, was permitting them to accumulate in the food chain. Non-target species, such as fish and birds, were found to contain DDT concentrations 10,000 times the environmental background. Along with DDT, the non-biodegradable PCBs also began to show up in the environment. In this program, we'll examine the incidental production of dioxin and see what happens when scientists play dice with the elements. In a single organic substance, chemists shrugged off defeat by suggesting that the vital flame in living organisms was needed to spark organic compounds into existence. But this theory of vitalism was to have a short shelf life. In 1828, the German chemist Friedrich Wöhler stumbled upon something only the prepared mind could seize. Heating an inorganic substance, ammonium cyanate, he produced crystals, identical to crystals he had seen in urea. With his declaration, "Urea without the kidney," he shattered the theory of vitalism. Now, chemists scrambled to isolate organic substances and quickly identified a bewildering array of organic formulas. So bewildering that Wöhler threw up his hands and decried, "Organic chemistry is a dreadful jungle with no way out." Still, without a roadmap, chemists did come across signposts. Carbon was the common factor in organic compounds, and only a few other elements, such as hydrogen, oxygen, and nitrogen, were involved. Chemists were, however, perplexed by the large number of atoms forming organic molecules. The clearing was hacked out mid-19th century by another brilliant German, Friedrich Kekule. Theorizing that there was no distinction between organic and inorganic substances, he assigned to the so-called organic carbon a valence of 4, the same as its inorganic species. At the time, valence meant the power of an atom to combine with another atom. Since methane had been massed, Kekule knew its molecular formula, or the combining ratio of its two elements. He speculated that carbon, with a valence of 4, and hydrogen with a valence of 1, bonded in this manner. As for ethane, he proposed that carbon linked up with another carbon atom, while the remaining valences were satisfied with 6 hydrogen atoms. Structures began to emerge. One molecular formula could account for straight chains and branched chains as well. But they weren't out of the jungle yet. benzene, a stable compound with molecular formula C6H6, just didn't mesh with his proposed structural models. So, as any self-respecting chemist would do, Kekule slept on the problem and dreamed of atoms twirling like a snake until it seized its own tail. Eureka! With a flash of insight, he envisioned carbon atoms forming a ring, double bonded in this stable configuration. Kekule's elegantly simple structural formulas and his notion that carbon forms 4 bonds, now called covalent bonds, have stood the test of time. To answer what covalent bonds are and why carbon forms them, we must probe deeply into the structure of the atom. In this program, a 2-dimensional planetary model is most useful for our purposes. An atom consists of a nucleus containing positively charged protons surrounded by shells of negatively charged electrons. In helium, for example, 2 electrons circled the nucleus, the maximum allowable for the first shell. Neon possesses 2 electrons in its inner shell and 8 in its outer shell, the maximum permissible for the second shell. These atoms are self-sufficient and extremely unreactive. Lithium, like helium, contains 2 electrons in its inner shell, but only 1 electron in its second shell. Lithium then has a strong tendency to shed this electron in order to attain the stable electron configuration of helium. Enter fluorine. With 7 electrons in its outer shell, it's eager to strip an electron from lithium and attain neon's stable configuration. Lithium fluoride, an attraction of opposites, a marriage made in heaven. In molecular bonding, the measure of an atom's ability to attract electrons is referred to as electronegativity. On the periodic table, lithium, with its loosely held outer shell electrons, is assigned a value of 1. Fluorine, with its more tightly held outer electrons, an electronegativity value of 4. Carbon, halfway between the 2 extremes, has an electronegativity of 2.5. Its inner shell contains 2 electrons, and its outer shell 4. Carbon appears to have a choice in attaining maximum stability. Shed 4 electrons in order to resemble the lean, mean helium, or snap up 4 additional electrons and attain the heavyweight status of neon. But neither option is open because carbon's 2.5 electronegativity is too strong to relinquish 4 electrons and too weak to strip 4 electrons from other atoms. So in order to gain the stable configuration of neon, carbon compromises. It time-shares electrons with other atoms. Except time-sharing occurs nearly at the speed of light. The covalent bond then is defined as sharing a pair of electrons. Kekule had it right over 100 years ago, and his seminal idea is still the cornerstone of organic chemistry. While this 2-dimensional modeling is still useful, it has been superseded by 3-dimensional models, which we will explore in subsequent programs. In 1858, Friedrich Kekule presented science with the first workable model of the carbon atom. This is the classic representation of the simplest organic molecule, methane. Though revolutionary for its time, it has long since been superseded by today's more sophisticated model, patterned on the quantum theory of the atom. Quantum theory is based on wave mechanics, and this model is one of many modern visual renditions of methane bonding. In the planetary view of the electron shell, it was convenient to imagine electrons circling the nucleus in distinct pathways. Alas, nature doesn't work that way. Rather, experimentation reveals that there is a 90 to 95% probability of locating an electron anywhere within a region of space surrounding the nucleus. This cloud-like region is called an orbital. In this orbital model, the first energy level for any atom is called the 1s orbital, and it contains a maximum of 2 electrons. The filled 1s orbital for helium, or any other atom, is spherical and non-directional. In the planetary view of neon, the second energy level contains a maximum of 8 electrons. Since these electrons don't really move in perfect circles either, we'll transform them into orbitals. As we have just seen with helium, neon's 1s orbital takes on a single spherical shape as well. But the second shell is going to prove a little more complicated, as it is subdivided into 2 related types of orbitals. A 2s spherical orbital containing 2 electrons, and 3 distinct 2p orbitals, each occupied by 2 electrons. Unlike the 2s orbital, however, the 2p orbitals each contain 2 lobes, which somewhat resemble dumbbells. So far, so good. But since we have separated the orbitals for the sake of clarity, we can now regroup them around the nucleus. Notice the definite orientation of the 2p orbitals. In order to minimize the repulsion between electrons, the orbitals are aligned along 3 axes at right angles to each other. Now, we'll bring back the 1s and the 2s orbitals, which we temporarily orphaned, and surround the nucleus with all orbitals. Note that the electrons in the 2p orbitals would be, on the average, farther from the nucleus than the electrons in the 2s orbital. Because the energy of electrons increases as their distance from the nucleus, the 2p electrons are in a slightly higher energy state than the 2s electrons. Now, if you didn't quite see this energy difference, you're in good company, since this orbital model tends to become cluttered. Nothing sacred about models, so we'll dismantle the component parts once again. On a simplified scale, the relative energy levels of the electrons show up this way. And it's this view of the distinct energy levels of the 2s and 2p electrons that will help us understand the behavior of carbon. But first, we will call up the planetary model of carbon with its separate shells and begin to transform them into orbitals. Because the 2 electrons in carbon's 1s orbital don't play a role in molecular bonding, we can mercifully dismiss this orbital. But carbon does possess a 2s orbital with 2 electrons and 3 2p orbitals containing the remaining 2 electrons. No, you're not going mad. You heard correctly. 3 orbitals containing 2 electrons, which raises the interesting question, what occupies the third orbital. Quantum theory is as quirky as a slot machine. Only two of these 2p orbitals can be occupied by an electron at any moment. But which orbitals, we can't say. Now, we will temporarily assemble carbon's 2p orbitals and its 2s orbital. In carbon's ground state, these related orbitals are at two distinct probability distances from the nucleus, which puts the 2p electrons, on the average, at a slightly higher energy level than the 2s electrons. Yet, when carbon bonds with hydrogen to form methane, empirical evidence insists that all four bonds are of equal energy. The solution to the paradox? Save appearances, save the model, and blend or hybridize the orbitals with a jolt of energy. Four entirely reformed orbitals of equal energy, all equidistant from the nucleus. We can theorize how hybridization occurs by returning to carbon's ground state, dismembering the model, and mounting the bonding orbitals on the energy scale. With a boost of energy, one of the electrons in the 2s orbital is kicked into an empty 2p orbital. Simultaneously, while the remaining 2s electron is booted up to an intermediate energy level, the electrons in the 2p orbitals drop down to its equivalent energy level. Now, we'll reassemble these hybridized orbitals to a three-dimensional model. These bowling pin orbitals are now given the shorthand designation sp3, where the S and the P indicate their hybrid nature. And for you sports fans who love instant replay, we can imagine the lightning speed hybridization taking place this way. A 2s electron jumps into a vacant 2p orbital, and instantaneously, all four orbitals transform into shapes of equivalent energy. Again, all four hybridized orbitals have the same size and shape and are pointed towards the vertices of a tetrahedron. At 109.5 degrees, the electrons have optimized their mutual repulsion. Now to continue. Since each sp3 orbital contains only one electron, it can accommodate one more electron in a covalent bonding arrangement. And hydrogen, with an eager electron in its 1s orbital, is a good candidate with which to share electrons. Hydrogen orbitals can hardly resist overlapping with carbon's orbitals to form methane, a stable molecule with four covalent bonds. In the next program, we'll watch carbon, the Lamborghini of the chemical world, put on a spectacular performance. In Program 2, we examine the sp3 hybridization of carbon's orbitals and electrons. In the case of methane, the hydrogen orbitals overlap with carbon's hybridized orbitals to form four covalent bonds. These bonds are called sigma bonds, and sigma bonds are relatively stable arrangements. Carbon bonds to a variety of atoms, including other carbon atoms. This is the structural formula for ethane. The carbon-carbon sigma bonds can be visualized taking place in this manner. Two carbon sp3 orbitals overlap, while the remaining sp3 orbitals overlap with hydrogen to take on this configuration in ethane. So far, we have examined only single sigma bonds. But how do carbon atoms form double bonds indicated by the structural formula for ethylene? To find out, let's first return to carbon in its ground state. As any good conjurer, carbon has another quantum trick up its sleeve. Voila, a new hybrid state. Notice that this hybrid model has a different structure than the hybrid model with the sp3 orbitals. It is this specific, different hybrid state that will explain the nature of the double bond. To understand how this hybrid state was formed, let's take carbon in its ground state and use an energy diagram, reminding ourselves that what we're assembling is pure hypothesis. Carbon contains 2 electrons in its 2s orbital and 2 electrons in its 2p orbitals. With a shot of energy, an electron in the 2s orbital is booted into a vacant 2p orbital. Simultaneously, the remaining 2s electron is promoted to a higher energy level as a pair of 2p electrons drop to this intermediate level. These hybridized orbitals are designated sp2, and their electrons are called sp2 electrons. The sp2 hybridized orbitals are oriented on the same plane at 120 degrees apart, whereas the remaining 2p orbital is aligned perpendicular to this plane. What must be emphasized is that the electron in the 2p orbital is at a slightly higher energy level than the electrons in the sp2 orbitals. This hybrid state model now illustrates the double bond phenomenon of ethylene. In the act of bonding, these 2 sp2 orbitals overlap to form the now familiar sigma bond. The remaining sp2 orbitals form sigma bonds with hydrogen. One final step remains. The electrons in the 2p orbitals meld in this saddle-shaped arrangement. Now don't let this hurt your head, because the electrons are about to pull their usual quantum stunt. They alternate above and below the plane. The overlap of carbon electrons in the p orbitals is called a pi bond. So, when we use the structural formula for any carbon-carbon double bond, we must remind ourselves that the double bond is composed of both a pi bond and a sigma bond. It is the site of the pi bond that is most vulnerable to chemical attack. Pi bonds are weaker than sigma bonds because the pi electrons are, on the average, farther from the nucleus than sigma electrons. In molecules like ethylene, the pi bond keeps the hydrogens of the 2 carbon atoms aligned in the same plane. As well as acting like a straitjacket in this case, pi electrons are adventurous in ways that exceeded even Kekule's dreams. In his vision, benzene formed double bonds in this manner. Quantum mechanics, however, amplifies his vision. It accepts in general his rigid sigma bonds. But the pi bonds would be locked in place by Kekule's formula. Pi electrons instead escape their shackles Houdini-like. At a higher energy level than the electrons in the sp2 orbitals, they are not bound to specific pairs of carbons, but resonate in continuous rings. We've come a long way since Wohler declared that organic chemistry is a jungle. Out of the jungle has emerged the underlying architecture of carbon. And it's this architecture that provides science with a key to discovering over 1,000 new carbon compounds each year. As we explore some of the more useful compounds, plastics that reshape our culture, fuels that fire the engines of industry, synthetic fibers that support fashion and design. Don't be intimidated by the variety of formulas and models you will encounter. For example, in this type of space-filling model, we have depicted the overlap of the hybridized orbitals this way, so that carbon and hydrogen atoms clearly stand out. And the bonds are depicted as a definite overlap. Others argue a more realistic representation depicts the mutual absorption of the orbitals this way. Fine. When symbolizing molecules, chemists select the model which emphasizes that aspect of the molecular structure they wish to feature. Some even resort to childhood tinker toys. And when some atoms play a redundant role in a chemical reaction, just pull them off. In truth, space-filling models are not terribly useful beyond explaining the nature of bonding. With organic chemistry, we deal with macromolecules, and they would end up looking like a junkyard, when a structural formula is much easier to grasp. In science, the ultimate test of a model is whether it is useful, so simplicity is the dictum. More often than not, chemists are only interested in the reactive sites or a potential reactive site on a molecule. This is the formula for benzoyl peroxide. With a hit of energy, we now convert it to two free radicals. The result is an unpaired electron, the reactive site on each radical. Chemists love shorthand, and so replace the superfluous atoms with the letter R. Because this is television, well, we take a little license as well. Our short form for the radical is a sphere, to which we attach a ravenous electron. Later in this series, we will explore the scavenging action of this radical in 3 dimensions, the real world of atoms and molecules. Petroleum contains over 500 naturally occurring compounds. But what accounts for this remarkable diversity? Again, the key is carbon's adventurous bonding arrangements. Take C4H10. There are 2 different structural formulas that can be derived from this one molecular formula. And these derivatives are called structural isomers. We'll now convert these formulas into ball and stick models. These 2 structures are N-butane and isobutane. Let's lose the hydrogens. Now we can focus on the alignment of the carbon bonds. The carbon spine of N-butane is called a straight chain, while the bonding arrangement of isobutane is called a branched chain. However, a hydrocarbon with the formula C5H12 has 3 different structural isomers, so that what stands out is a straight chain, a branched chain, and yet another different branched chain. The isomers are distinct compounds with different boiling points. Pentane boils at 36 degrees. 2-methylbutane at 30 degrees. And 2,2-dimethylpropane at 9 degrees. Now, if the number of carbon atoms is increased to 6, a total of 5 different chain structures are possible. Furthermore, carbon also forms ring structures. A 6-membered ring, a 5-membered ring with 1 carbon attached, or a 4-membered ring with 2 carbons attached, oriented in at least 4 different ways. If you're beginning to sense that you're staring at an infinite number of possibilities, you're right. But let's come down to earth and see how industry prepares hydrocarbons for fuels. The small hydrocarbons, numbering up to 5 carbons, make up natural gas. Of the organic portion of natural gas, methane constitutes from 60 to 95%, while the balance is composed of ethane and propane. But natural gas also contains inorganic impurities, useful ones such as hydrogen sulfide, and a downright nuisance, water vapor. The trick with this gaseous cocktail is to separate what we need. Water, which forms hydrates and clogs pipes, must be removed. So the gas is compressed at ambient temperatures, and water is drawn off in a liquid state. Now, because hydrogen sulfide is a weak acid, it can be removed by absorption in a weak base such as monoethanolamine. Eventually, this salt is converted into sulfuric acid or elemental sulfur. The dried gas is then cooled to minus 45 degrees Celsius in order to condense out most of the hydrocarbons of higher mass. Methane is then piped into factories and homes, where it makes an excellent fuel. Crude oil, on the other hand, is a complex soup. And the generic term petroleum refers to that part of crude that contains hydrocarbons of intermediate length. These are the volatile fuels, which have specific domestic and industrial applications. As the number of carbons in a chain increases, so does the boiling point. Because the boiling point range for each product is different, hydrocarbons can be separated by a process called fractional distillation. So, as you may have already guessed, the first step in the separation involves boiling the crude stock. The crude is zapped with superheated steam, and the vaporized mixture enters the fractionating column, where the temperature decreases from the bottom up. The vapors then begin to condense as they pass upwards through a series of horizontal trays and bubble caps. Vapor containing heavier molecules, namely those with higher boiling points, condenses in the lower trays, while the lighter molecules, or those with lower boiling points, proceed to the next layer of trays. Note that when the liquid fills the tray, it overflows back down to the tray below, so that revaporization takes place numerous times to ensure a more refined separation. Finally, the liquid fuels at target boiling points are continuously drawn off. Whether petroleum made the car industry or the car the petroleum industry, from decade to decade, the consumer demands a different fraction from a barrel of crude. In the 1920s, the motorist got only 25% of a barrel of crude as gasoline. Currently, about 40% is needed, a proportion considerably larger than available through fractional distillation. So chemical engineers reach down deeper into a barrel of crude to draw off the heavier hydrocarbons, those in the C30 to C40 range, and shunt them into a catalytic cracker where they are broken down into smaller hydrocarbons. A catalytic cracker consists of a reactor, a regenerator, and a still. The heavy oil stock is vaporized, mixed with a catalyst, and sent to a reactor where the actual breaking down and reforming of molecules occurs. The catalyst is recycled from the reactor to the regenerator, where the particles are cleaned by burning off the carbonaceous coating. In the reactor, the catalysts help to cleave long-chained hydrocarbons into groups of short-chained isomers. The cracked mixture now enters the still, where it is separated into high boiling point components, which are recycled for further cracking, and low boiling point components, namely gasoline and refinery gases. In this manner, the petroleum industry continues to satisfy the changing demands of the consumer. The body extracts energy from whatever food enters the stomach. Our digestive machinery breaks down food into macromolecules, proteins, fats, and carbohydrates. Though energy is obtained from all three food types, carbohydrates usually provide the bulk of it. Carbohydrates are often long-chain molecules made up of repeating units of the sugar glucose, symbolized here in this form. Through the process of cellular respiration, enzymes within the cells break the chemical bonds in glucose, liberating its stored energy. To most of us, respiration means the exchange of oxygen and carbon dioxide in the lungs. But cellular respiration, occurring in individual cells, involves much more than just this gas exchange. For our purposes, the cell will simply consist of the cell membrane, nucleus, cytosol, and mitochondria. Each cell contains several mitochondria. Together, they provide the cell with energy to carry out its various functions. However, to avoid cluttering our model, we'll show just one mitochondrion. Inside, the mitochondrion has two lipid membranes and its own unique genetic material. The inner membrane is convoluted in a series of folds called cristae, which create a greater surface area where chemical reactions can occur. Beyond the inner membrane is the mitochondrial matrix, which, like the cell cytosol, is a fluid. Indeed, the mitochondrion, so crucial to powering cells, is organized like a simple cell. This observation prompted the thought that mitochondria may well be descendants of simple photosynthetic bacteria. It's theorized that about 1.5 billion years ago, these bacteria were absorbed by primitive cells. Surviving the cell's defense mechanisms, they divided on their own. And over time, they adapted their photosynthetic machinery to evolve the mechanics of cellular respiration. In fact, biochemists have uncovered startling similarities between photosynthesis and cellular respiration. Similarities supporting the hypothesis that plant and animal life have a common origin. Yet, while photosynthesis stores the energy of the sun in carbohydrates, cellular respiration reverses the process by releasing the energy of carbohydrates. The monumental breakthrough of cellular respiration produced the cell prototype for all plants and animals. These supercells ably converted raw fuel to useful energy and brought about the proliferation of countless types of life forms. Today, we take glucose obtained from the intestine together with oxygen from the lungs and transport them via the circulatory system to the cells. Once inside the cell, glucose and oxygen react to release energy, carbon dioxide, and water. Glucose carries a lot of energy, around 160 kilojoules per mole. Yet, two molecules attempting to come together may require as little as 1.2 kilojoules per mole of reactant. Thus, glucose as a direct energy source would be an extreme case of overkill. But the events occurring within the cell harness the energy of glucose by transferring portions of it to the energy-carrying molecules of adenosine triphosphate, or ATP. So, when two molecules require energy to react, ATP provides just the right amount of energy, about 1% of the energy of a glucose molecule, or roughly 1.8 kilojoules per mole. If we look closely at a molecule of ATP, we begin to understand how it plays such an important role in cell reactions. Adenosine triphosphate consists of the nitrogenous base adenine, the sugar ribose, and 3 phosphate groups. Though one might think it is the sugar which gives ATP its energy, in fact, it is the phosphate tail which provides the energy. And biologists often represent the tail's energy in this way, as a single pi energy bond. But it is actually the 4 negative charges localized in the phosphate groups that explains ATP's volatile nature. These charge groups have a strong repulsion for each other. But unable to overcome the bonds that join them, they create a highly energetic molecule. For our purposes, we will represent ATP like this, with cylinders symbolizing the 3 phosphate groups. When ATP and a molecule come together and react, the molecule picks up a phosphate group, leaving behind adenosine diphosphate, or ADP. With the transfer of one phosphate, ATP has spread its negative charges and transferred energy to the molecule. Having gained a phosphate, the molecule is phosphorylated. With the aid of an enzyme, the now activated molecule can undergo further change, releasing the phosphate and enzyme. By creating a phosphorylated intermediate molecule, ATP provides that vital link in the synthesis of a product. The ingredients are present and the stage is set. In the following programs, we will examine the 3 major phases of cellular respiration: glycolysis, the Krebs cycle, and oxidative phosphorylation. every living creature uses energy. While some burn it in a blaze of activity, others spin it out in a leisurely fashion. But for every life form, it takes energy to get energy. This maxim extends from the behavior of whole communities to the activities of a single cell. At the molecular level, energy comes in packets of glucose. As we saw in Program 1, the energy of glucose must be transferred to ATP. This energy transfer happens through the process of cellular respiration. Phase 1, glycolysis, initiates the release of energy from glucose. Since all organisms have similar methods of processing energy, biologists believe that most life forms have a common ancestry. While glycolysis is a complicated pathway, it can be reduced to a few essentials. Glycolysis initiates the release of energy by injecting the 6-carbon glucose molecule with sufficient energy to cleave it into a pair of 3-carbon molecules of pyruvate. In the process, 2 molecules of ATP are synthesized. Each reaction in glycolysis enlists the assistance of enzymes to take the reactants to products. There you have it, the bare bones. But before the process of glycolysis gets underway, glucose must be made available. In the human body, glucose is stored principally in the liver and muscles as the carbohydrate glycogen. So glycogen acts as the storehouse of glucose in the body. Upon demand, liver glycogen is broken down by enzymes into single glucose molecules, which are then transported by the circulatory system to organs and tissues. At the lipid membrane of a cell, glucose crosses through a protein tunnel and enters the cell cytosol, where glycolysis will take place. While the aim of cellular respiration is to provide an accessible reservoir of energy for the cell, the first half of glycolysis actually requires the input of energy. This energy is provided by ATP, which breaks the bonds of glucose. But as we shall see, the sequence of reactions in glycolysis will eventually produce a net gain of ATP molecules. Now for the details. In the first reaction, called phosphorylation, a phosphate group from one ATP is transferred to glucose, producing glucose phosphate and ADP. While half of ATP's energy was used in the reaction, the remainder is held in the energized glucose phosphate. The placement of the negatively charged phosphate group on the glucose confines glucose phosphate within the cell. In reaction 2, the committed glucose phosphate encounters an enzyme and is reshaped to fructose phosphate. In reaction 3, fructose phosphate reacts with a molecule of ATP, producing fructose diphosphate. Up to this point, glycolysis appears to be a fairly smooth process, with one reaction following another. Glucose consumes 1 ATP to form glucose phosphate, leading to fructose phosphate, and with the use of a second ATP, fructose diphosphate. While the steps seem straightforward, when we isolate the reaction of glucose phosphate to fructose phosphate, an apparent problem arises. Fructose phosphate is a highly unstable molecule that has a strong tendency to revert to glucose phosphate. Were the reaction reversible, glycolysis would grind to a halt. So, what keeps the reaction moving in one direction? The answer lies in the concept of reaction coupling. As each fructose phosphate is formed, an ATP immediately reacts to form fructose diphosphate. In this configuration, the stable fructose diphosphate does not revert to glucose phosphate. Now, like coupled boxcars, as each fructose phosphate is used, a glucose phosphate replaces it. And for each glucose phosphate used, a glucose molecule is brought into the cell. This coupling of reactions is the driving force for all of glycolysis. Let's pick up glycolysis in reaction 4. The 6-carbon fructose diphosphate is cleaved into 2 distinct 3-carbon molecules, DHAP and PGAL. In reaction 5, DHAP is converted into a second PGAL molecule. The 2 companion PGAL molecules now continue along the pathway. And that's it, the first half of glycolysis. Let's review the process. Glucose, glucose phosphate, fructose phosphate, fructose diphosphate, DHAP and PGAL, and finally 2 PGAL molecules. In summary, ATP infused more energy into the 2 PGAL molecules than contained in the parent glucose molecule. In the next program, we'll follow the fate of PGAL through the second half of glycolysis. While there is no fourth law of thermodynamics, there should be. It would state that energy is furtive and plays a shell game with nature. In cellular respiration, the trick is to find where useful energy is hidden. In the first 5 reactions of glycolysis, we followed the energy path from glucose step by step as it is split into a pair of 3 carbon molecules of PGAL. For the second half of glycolysis, bear in mind that although everything occurs in duplicate, we're going to track only one PGAL. We'll watch PGAL synthesize ATP and energize a molecule of nicotinamide adenine dinucleotide, or NAD. NAD is one of a group of intermediate energy carriers, which is used to generate ATP. Its complex structure is devoted to the transfer of energy. Here within this carbon ring, the positive charge represents an area of electron deficiency and drives NAD to snap up a pair of energetic electrons together with a hydrogen ion. In this form, the energized NAD molecule is called NADH. For simplicity, we'll represent the electron-deficient NAD as NAD+, and the electron-rich NAD as NADH. Now let's return to glycolysis. In reaction 6, NAD+ saddles a molecule of PGAL. And with the aid of an enzyme, NAD+ picks up 2 electrons and a hydrogen ion. The product is an energy-rich NADH. In this exchange, PGAL grabs a free phosphate to form diphosphoglycerate, or DPGA. Let's pause and look at the energy profile. Over the first 5 reactions, energy was cranked into the pathway. Now, in reaction 6, some of the energy of PGAL is shunted out of the pathway in NADH. Charged with 2 energetic, shall we say ambitious electrons, NADH is an excellent energy carrier. Recapping chemistry, PGAL, having released electrons, is oxidized. And NAD+, having gained electrons, is reduced. So oxidation reactions release energy, while reduction reactions store energy. Reaction 7. The molecule of DPGA encounters ADP. A phosphate is transferred to form ATP, leaving behind phosphoglyceric acid, or PGA. From here on, glycolysis is devoted to eking out just one more ATP molecule from the single PGA. On its own, ADP lacks the necessary energy to capture the phosphate, so a subtle rearrangement of the molecule occurs. Then in reaction 9, a molecule of water is lost, leaving phosphoenolpyruvate, or PEP. The bond holding the phosphate is sufficiently weakened, so that in the final reaction, ADP liberates the phosphate and makes the ATP we sought, and the 3-carbon compound pyruvate. Again, let's step back and place all these reactions in profile. Two molecules of ATP infused energy into the system. From there on, energy was extracted by 2 NADH molecules and 4 ATP molecules. So what was the net gain? 2 ATPs were consumed, 4 were produced. The net gain was 2. Of the energy contained in the original glucose molecule, these 2 ATPs account for only 2.2%. The bulk of the energy is distributed between NADH, pyruvate, and heat. With a 2.2% payload, glycolysis in and of itself doesn't seem like a very effective engine. But when it comes to simple organisms like yeast, it just about gets the job done. These organisms survive. More so, they thrive with just a modicum of effort. Let's see why. Return to reaction 6. PGAL donates electrons to NAD+. But yeast has a very limited supply of NAD+. So if the last of the NAD+ were used to make NADH, glycolysis would grind to a halt, and absolutely no ATP would be produced. Yeast then resorts to a further strategy. It offers up its pyruvate. Carbon dioxide is removed, forming acetaldehyde. Next, NADH converts acetaldehyde to ethanol, common alcohol. This reaction produces NAD+, which feeds back into reaction 6 and continues to synthesize ATP. The extra steps that yeast took is called alcoholic fermentation. For simple life forms, glycolysis, together with alcoholic fermentation, satisfies their simple needs. However, higher life forms have to squeeze a lot more energy from NADH and pyruvate to enjoy the good life. In the next program, we'll examine the mechanism for extracting even more energy from pyruvate.